In this video, we're going to go over section 4.3 from our textbook, and we'll start with the conjugate zeros theorem here. We see that if a polynomial function here, p of x, has only real coefficients, and if a plus bi is the zero of our polynomial function, then the conjugate a minus bi is also going to be a zero of our polynomial function. So we're going to use this in our next example here. We want to find a cubic polynomial function p in standard form with real coefficients having zeros 3 and 2 plus I that satisfies the requirement that our polynomial function evaluated at minus 2 will give us 4. Well, we just saw from the conjugate zeros theorem that if 2 plus I is a 0, then 2 minus I, its conjugate, must also be a 0 of this function. We also know that this function, p of x here, is going to be a cubic function. So because of that, this tells us that this function will have 3 linear factors. And by the factor theorem, we know that our factors are going to be, I'll list them, x minus 3, x minus 2 plus I, and x minus 2 minus I, right? Because these are the zeros for a polynomial function. So what we can do is write our function right? So that is our polynomial, let's say with these 3 factors here. And so what we'll do is multiply these guys. So we'll multiply these 2 first. So we'll have x minus 3 times, we'll get x squared minus 4x plus 5 here. Right? And you guys can check that just by distributing each term here to each term there. And then multiplying these 2 guys, we'll get x cubed minus 7x squared plus 17x minus 15. All right, but we also need for our polynomials to satisfy this requirement here. And so what we'll do is we'll make note of the fact that if we were to multiply our polynomial by any constant number, maybe we'll call it a, this will also yield a function that satisfies the given conditions that we just talked about. So having these 3 factors here and this requirement here. So what I mean is, we can multiply our polynomial function by some constant. We said we're going to call it a. And it won't change the given conditions of this function. Then what we can do is use this here to solve for a. So we'll plug minus 2 into our polynomial function. And this is going to be equal to 4. So then we'll get a times, we'll have minus 8 minus 28 minus 34 minus 15. So this is going to be equal to 4. So then we'll get a times minus 85 is equal to 4. And then solving for a, we'll get 4 over minus 85. So a cubic polynomial function that satisfies the conditions is given by this here. Alright, so let's look at one more example. In this case, we're not going to be dealing with complex zeros. We want to find a polynomial function p of degree 3 with real coefficients that has these zeros here and satisfies this condition. So we know that if our polynomial has these zeros here, then our polynomial can be rewritten as x plus 3 times x plus 1 times x minus 4, right? Just based off of these zeros here. And the fact that our polynomial function will have degree 3, so we know it's going to have these 3 factors. multiplying this, we'll get x squared minus 3x minus 4, which is going to be x cubed minus 13x minus 12 when we multiply it by that x plus 3 term there. Alright, and just like we saw in the last example, the general form of this polynomial, which also satisfies these conditions, is going to be this here. And we'll do the same thing. We'll evaluate our polynomial at minus 2 and use the fact that its output is going to be minus 3 to solve for a. So here we'll get minus 8 plus 26 minus 12 times a is equal to minus 30. So this tells us a is equal to positive 6. A times 6 is equal to minus 30, so a is going to be equal to minus 5 by dividing by 6 on both sides. So the final polynomial, which meets all of the requirements that we just saw, is going to be the following. Minus 5 times x cubed minus 13x minus 12. Alright, and then we can also distribute this 5 to each term here if we want to, and then we'll get minus 5, I'll write this out, minus 5x cubed plus 65x plus 60. So just be careful with MyLab math. It might say that your answer is wrong if you have written it in this form. Try again by distributing this term to each term here, and it might accept this answer instead. Alright, so now we're going to look at the multiplicity of a 0. So the multiplicity of a 0 refers to the number of times a 0 appears. So for example here, looking at this polynomial, once it's factored, we have x times x plus 2 squared times x minus 1 cubed. So this tells us, since we have this x out here, we're going to have a single 0 of 0 there. Plugging in 0 for this x here will just give us 0. Then looking at x plus 2 here, we see that we have this term twice. We have x plus 2 squared. So this 0 will be of multiplicity 2. And similarly, for this x minus 1 factor here, we have that factor 3 times. So this guy is going to lead to a 0 with multiplicity 3. A 0 of 1 with multiplicity 3. So, multiplicities of zeros tell us a lot about the graphs of our functions. So for example here, this is what our graph looks like at a 0 if the graph crosses the x-axis for a 0 of multiplicity 1. Similarly, we'll have this case here. The graph is tangent to the x-axis at this point here if k is a 0 of even multiplicity. And lastly, the graph will cross and is tangent to the x-axis at that point if k is going to be a 0 of odd multiplicity that's greater than 1. So we'll use this information to do this example here. We want to draw a rough sketch of the graph of this polynomial function here, and we have it broken into these factors here. So I'll start with writing down what we know. These are going to be the zeros of our polynomial function. Let's look at the leading term, because remember that's going to tell us the end behavior of our polynomial, and our leading term is 2x cubed. So remember, when we have a polynomial and its leading term is of odd degree here, and its leading coefficient is greater than 0, what happens is that as x goes to infinity, so does our function, so do our output values. And as x goes to minus infinity, our output values go to minus infinity. So if we have a function with a leading term like this, our graph is going to look like something like this. These are the end behaviors of our polynomial function. Okay, and that's from section 4.1, if you want to go back and take a look at that. Something else that we know is that all of our zeros here are of multiplicity 1. They only show up once. Okay, so in that case, our graph when it crosses the x-axis at those zeros is going to look like this here. And the last thing we'll take note of is the y-intercept of this guy. Looking at this polynomial function, it should be clear what our y-intercept is going to be, because we're going to find the y-intercept by setting x is equal to 0. So when we plug 0 into this function here, all of these three terms here go to 0, and we're just left with 25. So evaluating our function at 0, we get 25, and this is going to be our y-intercept. So with this information, we are going to graph a rough sketch of this polynomial. So the first thing we'll do is plot our zeros. We have minus 1, 5 over 2, and 5. So minus 1 is going to be somewhere right over here. 5 over 2 is going to be about right here. And 5 is going to be right about there. And remember, the end behavior of our polynomial is going to look like this here. So that means after the last 0, our end behavior is going to point in this direction. As x goes to infinity, so do our output values. So it's going to look like this. And then similarly for our last 0 over here, our polynomial function is going to go towards infinity as we increase our x values in this direction. So it'll look like that here. We also know that when our graph crosses the x-axis at our zeros, it's going to look like this here. So at each of these points, our graph's going to look something like this. And the last piece of information we have is that our y-intercept is going to be 0, 25. So about that point there. So what we can do is connect these guys and get a rough sketch of our graph there. And then in this region here, we're not really going to know exactly what happens to our graph without plotting actual points. So our graph could potentially look like this, but without plotting actual points, we won't know for sure. All right, so that is a rough graph of this polynomial here. All right, so the last thing we'll look at in this video is the rational zeros theorem. So we're going to have a polynomial function of this form here, where our leading coefficient a sub n is not equal to 0, and our constant term a sub 0 is also not equal to 0. So if p over q is a rational number written in the lowest terms, and if p over q is a 0 of our polynomial function, then we have that p is going to be a factor of our constant term here, and q is going to be a factor of our leading coefficient here. Okay. So we'll use this theorem here to do the following examples. So for this polynomial function here, what we want to do is list all possible rational zeros, find all rational zeros, and factor our polynomial function. So by this rational zeros theorem here, we know that p is going to be a factor of our constant term, which is 45 here, and q is going to be a factor of our leading coefficient, 15. Okay. We also know that because our function is, we have a cubic polynomial function here, this degree 3 here tells us that we're going to have at most 3 zeros. All right, so using our theorem here, we'll look at the possible values for P and Q and list them here. All right, so these are going to be factors of 15 and 45. So factors of 45 are going to be plus or minus 1, 3, 5, 9, 15, and 45. Similarly, factors of Q, or Q, possible values for Q are going to be factors of 15, so plus or minus 1, 3, 5, and 15. Now, any rational zero of our polynomial function in the form of P over Q, and remember this is going to be in lowest terms, is going to be of this form here. All right, and just want to emphasize that this is in our lowest terms here, because for example, we could have our P over Q be 45 over 15, and in that case, that's just going to be equal to 3, and that is covered in the fact that possible value for P is going to be plus or minus 3. All right, now these are just the possible values for P and Q, the possible zeros. And so that's what we did for part A. We just listed all possible rational zeros. But now we want to find all the zeros. So what we'll do to determine that is we'll evaluate our function at each possible value. And when we find that evaluating our function at that value produces a 0, then the x value will be a 0. So doing so, just in the interest of time, I'll tell you that when we evaluate our function at all of these possible zeros, the only ones that are actual zeros is 1 over 5, minus 5 over 3, and minus 9. All right. And then for part C, what we want to do is factor our polynomial function. So we'll use our zeros to do so. We have that x is equal to 1 over 5, minus 5 over 3, and minus 9. So that means our three factors are these guys here. But remember, the leading term for our polynomial function was 15 here. So what we'll do is we'll use the fact that if we were to multiply our polynomial function by a constant a, it will not change the given conditions, right? These will still be the zeros for our polynomial function. In doing so, we can let a be equal to our leading coefficient, 15. And so our polynomial function becomes 15 times x minus 1 over 5 times x plus 5 over 3 times x plus 9. All right. So what we'll do is we'll distribute this 15 by splitting it up. So we can write this as 5 times x minus 1 over 5 times 3 times x plus 5 over 3 times x plus 9, right? Since we're just multiplying everything through, we can split up this 15 to 5 and 3 here. And the reason we want to do that is because we'll get 5x here minus 1. When we distribute this 5 to each term here, this 5 here will cancel with this one. And similarly, when we distribute this 3 to both terms here, we'll get 3x plus 5. These 3's will cancel. And then we're left with this x plus 9 term here. And then we have our fully factored form of p of x. Something else to note here is that you might be asked to use the graph to eliminate some of the zeros, and we can easily do this by looking at both where the graph intersects the x-axis, right? These will be the zeros, and we can use the end behavior, right? So the zeros will occur in between the end behaviors of the graph. All right, so the last example we're going to look at is this one here. We want to find the zeros for this polynomial function here, and we'll do so using our rational zeros theorem. However, remember the rational zeros theorem says that holds if we have a polynomial with integer coefficients. And we can see here that we have a polynomial that has two fractional coefficients here. So in order to use the rational zeros theorem, what we'll do is we'll multiply everything by a common denominator, right? If we were to multiply this by a constant number, we saw that that doesn't actually change the value of the zeros of our polynomial function. Remember, that was when we were multiplying our polynomial function by some constant that we were calling a. So we'll do the same thing here. We can multiply our polynomial function by some number, and it'll be the common denominator that we find between our fractional coefficients here. And the reason being is because when we distribute this common denominator, in this case this 3, to every single term here, we'll get 3x cubed plus 7x squared minus 11x minus 5. And so what that did was it got rid of our fractional coefficients here. And so now we just have integer coefficients and our rational zeros theorem applies. So using our theorem, we'll see that our possible values for p and q are the following. For p, it's going to be our factors of this guy, and we're distributing 3 to every single term here, so this will be 15. We'll get 5 times 3. So it'll be the factors of 15, so that'll be plus or minus 1, 3, 5, and 15. And then for q, it'll be the factors of our leading coefficient of our leading term here, so that'll be 3. So we just have plus or minus 1 and 3. And lastly, the possible values for p over q in lowest terms. Because remember, we could have a value for p over q to be 15 over 3, but that is just going to be 5 in its lowest terms, and that's already covered as a factor in p here. So the only possible values for p over q in lowest terms are plus or minus 1/3 and plus or minus 5/3. And lastly, to find the actual zeros, what we do is evaluate p of x at these zeros. And when we do so, we see that the zeros are going to be -3, -1, and 5 over 3.